So far we've seen that torque is established when a force is acting at a distance away from a pivot point. We say that a torque can generate rotational motion. The picture you see in front of you shows a beam, a long horizontal beam that is hinged to a vertical wall. When I run the simulation, gravity takes over and the beam falls. Nothing unusual about that. Now let's remove gravity. So imagine we're in outer space. The wall is set up exactly like we explained. There's still a hinge between the beam and the wall. But now when I run the simulation, nothing happens whatsoever. The beam just remains stationary. In the previous case, it was gravity that was creating the torque. Gravity was acting down on the beam at a distance away from the hinge, and it caused a clockwise rotation. Once we remove gravity, of course, there is no torque. There is no torque in the clockwise direction. So we need to add a force to generate a torque. Let's have a look at how that force must be added to actually generate rotation. I'll place a force at the end of the beam. When the force is active, it'll be at an angle of 90 degrees to the beam. We see that when that force is present, the beam rotates. So here's what it was before, and as soon as I run the simulation, the beam starts to rotate counterclockwise because the force is directed upwards. Now what if I started that force at a slightly different angle? Now we see a force is directed straight to the left, parallel to the beam itself. When I run the sim this time, we see there's no rotation. The beam remains where it is. That's simply because there's no rotation generated. All I'm doing is generating an extra force on the hinge to counter the force to the left. The hinge is reacting by pushing back to the right. But the beam itself does not rotate because my force is not perpendicular to the beam. So there's another condition for torques. The force and the distance have to act at right angles to each other. As long as there's a component of the force that's got a right angle to it, you'll generate a torque. Let's look at another angle somewhere in between. And now we see we've got a force directed upward to the left. We see there is a component that's at right angles to the beam itself. There's also one that's parallel to the beam. The component of the force that's parallel to the beam will not generate any rotation, as we've just seen. The only one that matters is this component right here, the component that's perpendicular to the beam. So when I hit run, we would expect this beam to rotate counterclockwise. And it does. Let's try one more force. This force will direct downwards at an angle. The value of the force doesn't matter, but we want the angle to never change with respect to the x and y axis or the plane of the actual paper itself. So in other words, this little blue force is always going to remain at exactly this angle. What's going to happen to the motion of the beam? Let's watch what happens. When we run it, we see the beam starts with a rotational motion, as we would predict, in a clockwise direction, but eventually its motion stops. And it stops once the beam's angle is exactly the same as the angle of the force itself, because now the force is actually parallel to the beam, and it's not exerting any component that's perpendicular to the beam itself to create rotation. So when the force is in this position, its torque is 0. So it started with a torque. There was a component perpendicular to the beam at the top, but it ended in a direction that's exactly parallel to the beam, and the beam no longer rotates. So the long and the short of this is that if you're going to calculate a torque using force times distance, you must use the force that's perpendicular to the distance. Conversely, you could use the original force and use a distance that's perpendicular to that force. Let's have a look at how that looks. So if I've got a force acting down at an angle like this and I want to calculate the torque, I can use this component of the force and multiply it by the distance at which the force is acting. Or I can use the original force and multiply it by the perpendicular distance. All you would have to do is extend a line through that force indicating its original direction, and then find a line that's perpendicular to that line back to the pivot point. This distance right in here would be my perpendicular distance, and if I multiply that by my original force, I would also get a torque.